Hello students. So today we try to learn about ionization energy. What is ionization energy? You know, every atom have some internal energy at their ground state and they have a stable electronic configuration at their ground state. So if you want to remove an electron from their valence shell, then you have to provide some amount of energy to the atom. So the amount of energy required to removal of electrons from the outermost shell of a gaseous or isolated atoms known as ionization energy. That means in their ground state they have a low energy compared to their excited state, because neutral element or neutral atom is more stable than charged atom. So the amount of energy required to remove an electron from their outermost shell is known as ionization energy. Sometimes it is very easy task to remove an electron from the outermost shell. Sometimes it is very tough. For example, you know, group 1 and group 2 as well as the metallic element are stable in their positive oxidation state. That means after removal of 1 or 2 or 3 electron, they acquire a stable electronic configuration. So electron removal from this type of atom are very easy. Therefore, when you want to remove an electron from group 1 and group 2 metal, group 2 groups metal, then it is very easy. But in case of halogen group, you know, halogen group have 7 electron in their valence shell. So to acquire octet electronic configuration, they required one more electron. So now if you want to remove an electron from their valence shell, then it is very tough work, because they are stable when they gain an electron, but you try to remove a electron from the outermost shell. So they required more energy to remove electron from their valence shell. But it is clear that it required energy to remove an electron. So we can say the ionization energy means the amount of energy required to remove an electron from their outermost shell. Now if you want to remove one electron from the neutral state or isolated atom, then it is known as first ionization energy. That to remove one electron from the ground state or from the neutral state, you have to provide some amount of energy, then it is known as first ionization energy, which is actually denoted as IE1 or I1. Then after removal of one electron, it transfer into cation. For example, if you consider M is the atom and you supplied some amount of energy to remove an electron. So after removal of electron, it transfer into M plus, and the amount of energy required for removal of this electron is known as first ionization energy. Secondly, if we again remove an electron from this M plus cation, then this M plus cation transfer into M2 plus, that is divalent cation, and then again you have to provide some amount of energy. So this energy actually known as second ionization energy. Similarly, again if you want to remove a one electron from divalent cation, that is M2 plus, then again you have to provide some amount of energy, and this energy actually known as third ionization energy. You know, if the size of an atom decrease, then the valence electron are strongly bound by the nucleus. As a result, the size of the atom reduce. So, when the size of the atom is smaller, then the valence electron are tightly packed or tightly attached or attracted by the nucleus. Then they required more energy to remove a electron from their valence shell. Similarly, if the atom size is larger, then the valence electron are loosely bound by the nucleus. Then you can easily remove the valence electron from their valence shell. So they are required less amount of energy. Therefore, so there is a relation between the size of the atom and the ionization energy. If the size of the atom is smaller, then they are required more ionization energy. And similarly, if the size of the atom is larger, then they are required less amount of energy. So you know, the size of M plus, M2 plus and M3 plus. Here, the size order of this cation follow that M3 plus have smaller size than M2 plus, as well as M2 plus have a smaller size than M plus, because you know, if the oxidation number of the atom increase, then the size of the atom reduce. Therefore, the ionization energy 3, that is third ionization energy, is more than second ionization energy, as well as the second ionization energy more than first ionization energy. So the order of ionization energy is IE3 required more energy than IE2 than IE1. Though there are some factor on which this ionization energy actually depend, because sometimes some atom have stable electronic configuration, that is half filled or full filled. If any atom have half filled electronic configuration, then you know it is very stable electronic configuration, then they require more energy to remove one electron. Similarly, if an atom have a full filled electronic configuration at their valence shell, then again they are required more energy to remove electrons. For example, carbon, nitrogen and oxygen. You know, the size order of this element is oxygen have smaller size than nitrogen than carbon. So the size order is carbon have a larger size than nitrogen than oxygen. So according to relation between size and ionization energy, that you know that size is inversely proportional with the ionization energy. If the size is shorter, then the required more ionization energy. So here the size of the oxygen is smaller than nitrogen, so the ionization energy of oxygen is more than nitrogen, but it is actually not happen. You know, nitrogen have half filled electronic configuration, that is 1s2, 2s2 and 2p3, that is half filled p orbital present in their valence shell. So they required more energy to remove an electron from this nitrogen atom. Similarly, oxygen atom, though the size of the oxygen atom is smaller than nitrogen, but you know, when oxygen remove an electron, then it gain a half filled electronic configuration, that is, you know, oxygen electronic configuration of oxygen is 1s2, 2s2 and 2p4. If oxygen remove an electron, then it transfer into 1s2, 2s2, 2p3. It is very stable electronic configuration. Therefore, it required less energy than nitrogen atom to remove electron. So the actual ionization energy order, or the first ionization energy order of nitrogen, oxygen and carbon is Nitrogen required more energy, therefore it required more ionization energy. So the actual first ionization energy order is nitrogen greater than oxygen, then carbon, because oxygen is smaller size than carbon. So the order, first ionization energy order is nitrogen, oxygen and carbon. Similarly, if we add fluorine to this series, then fluorine has smaller size compared to this atom. So the actual ionization energy order of fluorine, nitrogen, oxygen and carbon is fluorine greater than nitrogen, greater than oxygen, greater than carbon. It is the actual first ionization energy order. Then it is second ionization energy order. What is the second ionization energy order? Second ionization energy means after removal of electron, this all atom transfer into cation. Then the electronic configuration of fluorine is 1s2, 2s2, 2p5, but after removal of one electron, it transfer into fluorine plus, that is the valence electronic configuration is 2p4, whereas the nitrogen plus have electronic configuration is 2p2, and similarly the oxygen plus have electronic configuration, valence electronic configuration is 2p3 and carbon plus is 2p1. So here oxygen plus have half filled electronic configuration. That means it required more energy to remove electron from the outermost shell. Therefore, the second ionization energy order is oxygen plus greater than fluorine plus greater than nitrogen plus then carbon. It is the actual order of ionization energy. So, if the size of the element reduce, then they are required more ionization energy. But in case of half filled or full filled, it is more stable electronic configuration, so they required more ionization energy. Next, we try to learn about electron affinity or electron gain enthalpy. So first, what is electron gain enthalpy? Actually, if you transfer a neutral element or atom into anion, then this atom released some amount of energy, just opposite of the ionization energy. So the amount of energy released when an electron added to their valence shell, then this amount of energy actually known as electron gain enthalpy or electron affinity. For example, if X is a neutral atom, then if we add one electron to their valence shell, then it transfer into X minus, that is anion, and it also released some amount of energy. So this energy actually known as electron gain enthalpy or electron affinity. Actually, electron affinity is directly related with electronegativity. If the electronegativity of an element is increased, then electron affinity also increase, because electron affinity means the power of attraction of electron, and electron affinity means just added one electron to their valence shell. So it is quite similar but not exactly similar or same. So if the electronegativity of an element will increase, then the electron affinity of an element or atom also increase. Similarly, it is also related with the size, because when the size of an element increase, then the attraction of the valence electron and nucleus actually decrease. As a result, if you want to add one electron to the valence shell, then it is very tough, because there present less attraction force. So if the size of an element or atom increase, then the electron affinity also decrease. Therefore, here also a relation between size and electron affinity. If the size increase, then electron affinity decrease. Sometimes there is some exception, that is the size order of oxygen and sulfur. that oxygen have smaller size than sulfur. Similarly, you know nitrogen and phosphorus, that is nitrogen have smaller size than phosphorus, and also chlorine and fluorine, that is chlorine have higher size than fluorine. So electron affinity order should be fluorine greater than chlorine, or oxygen greater than sulfur, or nitrogen greater than fluorine, but actually it is not happen. Actually, the third period element always have higher electron affinity than second period element, that is chlorine have more electron affinity than fluorine, as well as sulfur have more electron affinity than oxygen, and also phosphorus have more electron affinity than nitrogen. Why? Actually, this exception arises due to the size of the valence shell. You know, nitrogen, oxygen or fluorine, they present 2p orbital to their valence shell, and for phosphorus, sulfur and chlorine, they present 3p orbital to their valence shell. So if you add one electron extra to their valence shell, due to the smaller size of 2p orbital, they produce a electron-electron repulsion, and due to this repulsion, the electronic configuration of fluorine or oxygen or nitrogen quite unstable. But in case of chlorine or sulfur or phosphorus, as their electron negativity less than those atoms, but when one electron added to their valence shell, then there no electron-electron repulsion produced. Therefore, after adding one electron, the electronic configuration is more stable than fluorine minus or oxygen minus or nitrogen minus. Therefore, the electron affinity of chlorine is more than fluorine, as well as electron affinity of sulfur more than oxygen. Similarly, the electron affinity of phosphorus more than nitrogen. And it is very important question also, that why chlorine have electron affinity, more electron affinity than fluorine, as well as why sulfur have more electron affinity than oxygen. It is very important question. But in general, if the size of the element increase, then the electron affinity of the element decrease. Similarly, if the size or electron negativity of an element increase, then electron affinity also increase. Next, oxidation and reduction. You know what is oxidation? Oxidation means loss of electron. That means if an element released one electron, then this reaction actually known as oxidation reaction. So, you know, group 1 and group 2 metal, when released electron, then they acquire a stable electronic configuration. So for them it is very easy that after removing electron, this occurs stable electronic configuration. So this element participate in oxidation reaction, and their valence electron easily oxidized. But in case of fluorine, you know, when fluorine gain a electron, then they acquire a octet electronic configuration. So they cannot remove electron from their valence shell, rather than they accept electron. So the valence electron are strongly binded for fluorine atom, therefore they slowly oxidized. So the group 1 and group 2 metal, that is alkaline metal or alkaline earth metal, act as a strong reducing agent because they oxidized itself, so they reduce other. So this element actually act as a strong reducing agent, whereas this fluorine, oxygen, this element are reduced easily, because reduction reaction means removal of electron. Reduction reaction means gaining of electron. Therefore, after gaining one electron or two electron, they are stable, so they easily reduce. So if they easily reduce, then they oxidize other. So this fluorine and oxygen atom act as a good oxidizing agent, whereas alkali or alkaline earth metals act as a good reducing agents. And in general, all metals are easily oxidized and more reducing power, and all non-metals are easily reduced and more oxidizing power. Thank you.